Okay, so today our presenter is Joe Kinrade from Lancaster University. So Joe is a research fellow in space and planetary physics at Lancaster University, specializing in auroral and plasma dynamics within Saturn's magnetosphere. His research focuses on remote sensing and imaging science using ultraviolet and ENA imagery from Cassini. He is a co-investigator on an upcoming Hubble Space Telescope campaign to observe Saturn's auroras. Joe earned both his MEng and his PhD in electronic engineering from the University of Bath. His doctoral research used GNSS tomography to image Earth's high-latitude ionosphere, including fieldwork in Antarctica and the first evidence that auroral arcs can affect GPS accuracy. For this work, Joe was awarded the Ede and Ravenscroft Prize for Best Postgraduate Research. He later held a Marie Curie Fellowship in Paris, profiling ionospheric scintillation for airport navigation systems, and was a visiting research fellow at the South African National Space Agency. So today, Joe's seminar is going to be what can energetic neutral atoms tell us about planetary magnetospheres? So I'll hand over to you now, Joe. Okay, great. So I can see your screen.
Yeah,
Okay,
thanks,
thank you.
thanks, Rosie. You hear me okay? Sorry
Yeah,
for making you
perfect.
read out probably the too long version of that bio. Thanks.
No, it
Um,
was great.
yeah, thanks everyone for coming to watch this seminar. I've been meaning to do this for ages, and in fact, Beatrice and Jasmine invited me ages ago to do one of these, and I've not been able to do it till now. Apologies, I've only got one screen, so I can't see my notes, so I'm just going to talk through this. And I was definitely too ambitious in my abstract in terms of reviewing ENAs across the solar system. So I'm going to try and stick to magnetospheres, particularly Saturn, which is what I work on. So the title, what can energetic neutral atoms, or ENAs, tell us about planetary magnetospheres? And if you take away anything from this talk today, I suppose it's that they're kind of an underutilized tool that we can use for diagnosing magnetospheric physics. And hopefully you'll come away with the knowledge of what these kind of donut tori plot is that we produced after lots of work at Saturn. So just to very quickly say what an energetic neutral atom is, or an ENA. The term ENA is starting to creep in, particularly in American conferences, but Don Mitchell calls it an ENA, so I'm going to be consistent with Don, who's something of a godfather of ENA detections. Essentially, a trapped singly charged positive ion charge exchanges with a neutral gas atom or molecule. And this can be solar wind ions charge exchanging with exosphere stuff, or at Saturn, it's injected plasma charge exchanging with water constituents, for example. And essentially it nicks an electron. And the cool thing is that most of the energy is maintained in the ENA, but it whizzes off at the trajectory that the charge exchange happened at, because it's no longer bound by magnetic field. So we can detect these things kind of like a camera detects a photon, except it has an energy and a chemical footprint as well. So they're very useful things to detect. Why do we want to detect them? I kind of think of these things as tracer particles for ongoing charge exchange processes, namely ion loss. And if we can detect them, which we'll come on to, it allows us to image very large-scale global dynamics, which are normally pretty much invisible to us. This stuff is typically measured in situ by single spacecraft or multiple spacecraft. But if you can do this and detect these things in a wide area, it really gives you some global context, and it helps us to constrain ion and neutral populations as well, which is obviously very useful. And we're starting to understand relationships that ENAs have with other phenomena in the magnetospheres, like auroral activations, rotating signatures, and also radio emissions as well, which I'll touch on briefly today. The images on the right-hand side are from Edmund Roloff, who is one of the pioneers in ENA detectors and their development. Way back in the 70s, these images were taken. The top two are simulations of Earth's recurrent ion population. On the right-hand side is a sort of model of the ENA emission. And then the two below that are predictions of what the sensor was going to see. And then the bottom image is what was actually captured. So a really nice plot where the intent and then the success is there in just those four images. The reason it's impressive is that even back in the 70s and even today, actually, that neutral stuff's really hard to detect in space, right? So detecting the water Enceladus, for instance, we kind of knew it was there from magnetic deflections, but actually detecting the neutral stuff directly with a spacecraft instrument is really hard. And people like Don Mitchell and the APL team and teams in Sweden as well were thinking about this back in the 60s and 70s. And to detect neutral stuff, ENAs, you need a time of flight instrument. And this is the INCA camera, which is kind of a classic example. It's really a pioneering instrument. At a very basic level, you have charge plates. And the idea is you're sweeping away anything that's charged. So anything that comes through those slits is going to be neutral. And then there are a series of foil plates where you have a start time and a stop time. You have your angle discrimination from the fan of the plates. And then essentially you can get the direction that the things come in at, you get the energy spectrum, you get a very coarse composition. So whether it's oxygen or hydrogen, for example. So that's kind of a very quick overview instrument-wise for any fans of instrumentation. The geometry of capturing an image is something like this. So using Saturn here as a classic case where we have uniquely in our solar system a spin-aligned and a magnetic dipole axis. And we have a plasma population sort of embedded within this extended neutral cloud. So Saturn's sometimes referred to as kind of an ideal ENA emitter in terms of a planetary magnetosphere. But the geometry here, you can see we're always taking a line of sight integral as a function of the ion population, the neutrals, and the charge exchange cross section as well. But just remember that it's always a function of both the ion and the neutral population. So we tend to have an assumption at Saturn that the neutral cloud is very slowly changing with respect to the ion populations, and also that it's quite smooth. But in reality, we know it's quite structured. But that's an assumption that we make in producing these images. I'm going to skip ahead to kind of show, this is kind of the latest picture that we have. These are probably some of the nicest projections you'll see in the solar system at the moment of magnetospheric ENAs. This is a top-down equatorial projection looking at Saturn with the sun towards the bottom. And it's a series of projections covering a few days back in 2007. But it's very typical of what we see at Saturn's magnetosphere. You have these huge rotating enhancements in the ENA intensity that go around the planet, multiple rotations. Sometimes you get multiple activations happening as well. And they're signatures of large-scale plasma injections from the magnetotail. And we'll talk a little bit about the Saturn system afterwards. A very quick review, I realized as I started to review ENA emissions of other planets that I'd been too ambitious, but I'm going to quickly talk about things I'm not going to talk about, if that makes sense. So I'm not talking about ENA sputtering today, although it's very cool. There are entire AGU sessions on sputtering, and essentially what we're looking at here is solar wind particles reacting directly with the surface of atmosphereless moons or bodies like Mercury, for example. This is the moon here. So you have a sort of a solar wind impact and a reflection, and then the kind of the dust and the regolith, I really like the word regolith, charge exchanges there. So you have a subsolar point sort of signature of ENAs being emitted off the moon. And there are terms like ENA albedo and things associated with this that we might not see so much in the magnetospheric context. So I'm not talking about those today. Thinking about planets in the solar system that have weak or induced magnetospheres, Mercury likely, yes, has this sputtering, but also it has this, we know it has this dynamic, very complicated induced magnetosphere. So there's going to be a complex mix there, and these are predictions on the right-hand side of the moon's ENA emission, which is a simpler case, and on the bottom a simulation of Mercury's potential ENA emission, which is a combination of surface impact and sort of exosphere stuff. The same Venus Express also detected ENA emissions associated with Venus's exosphere as well. And Mars is arguably even more complicated. It's a complex mix of exosphere, surface impact, but there's also some evidence of crustal field ordering as well of ENA emissions associated with solar wind stuff getting into the tail. I don't know how that works exactly, but the concept, you'll see the term ENA sounding associated with ENA emissions at Mars, which is something I've not seen before. And that's a potential tool for exploring the solar wind exosphere interaction at Mars. So on to sort of strong magnetospheres. We'll see a bit more of Earth in a second, but that's how all of this developed, really, looking at Earth's ring current back since the 70s. Jupiter is an exciting time to be thinking about ENAs at Jupiter because we have JUICE on the way with advanced ENA cameras. And we know that moon tori exist at Jupiter, which is likely going to have ENA emissions. And Saturn is kind of the poster child for planetary magnetosphere ENA emissions as well. And Uranus and Neptune, very briefly, question marks, unknown. So, bit of history, looking at the origins of ENA detecting at Earth. They were first detected from the IMP satellites and the ice emissions back in the 70s. This paper from 1985 shows a correlation with storm time DST index and the count rates in the Earth, looking in the Earth azimuth direction, which is where those two arrows are, if you can see that. And essentially that's solar wind ions coming in and charge exchanging with sort of enhancing the ring current and then charge exchanging with the exosphere. So that's a very cool early ENA detection way back in the 1970s. And similar results followed with a Swedish microsatellite, Astrid, an early paper from Pontus Brandt, who's now PI of the JUICE ENA images. Moving the Earth picture on a little bit, we have stereoscopic ENA imaging from the TWINS mission as well. So looking at the ring current from different angles, kind of low resolution, but it gives you asymmetries at different sides of the planet, which is very hard to do from single spacecraft. And speaking of JUICE, it just took this amazing high resolution image of Earth's ring current on its way out. So that's kind of a new result, really. And people that understand the ring current will know that, yeah, they imaged basically plasma injections associated with substorm dynamics. So actually taking pictures of this from space, which is pretty cool. So moving on to Saturn, which is sort of more my comfort zone. Some of you will have seen this artist impression before. And it's actually based on about 3 years of particle pressure data from Cassini. You can look at that data in this Chromigus Nature paper. It's a really nice illustration of a giant planet magnetosphere. I think you can see things like particles being guided on the field. You can see the solar wind distortion. But the thing that's interesting here, that when I first saw this, was this orange torus of the dense neutrals, the deep inside Saturn's magnetosphere, associated with Enceladus. And then you also have this extended plasma sheet as well with the ion population. So kind of zooming in to the source of this neutral torus, I think this is probably one of my favorite things that Cassini did. It's a movie of the water ice plumes coming out of the south pole of Enceladus. And this tiny moon is the source of all the water constituents deep in Saturn's magnetosphere, and it has huge implications for ENA production, as we'll see. So a super quick review of why internal mass-loaded magnetospheres are kind of different to Earth. So Michelle Thompson did this really nice short paper on mass loading and rotation dynamics. Many other people have worked on stuff like this as well. It's just had a nice conceptual plot in this paper. So you have internal plasma being thrown out through the magnetosphere due to centrifugal forces and things like radial interchange transport, radial transport as well. And occasionally, to maintain system balance, mass has to be lost down the tail. So this side view kind of shows a cross section through one of these fingers, if you want to call it that. But not all of the plasma is lost down tail. Some of it gets accelerated back to the planet under magnetic tension, and the plasma is heated and returned to the inner magnetosphere, and that's where we can detect things in ENAs, also things like auroral signatures, dipolarizations, and as well. So kind of jumping straight into what these things look like in the ENA images. This is an early result from Don Mitchell, and what we've got here are essentially 4 photographs taken from quite inclined orbits from Cassini INCA, and you can see kind of an activation that comes around from the night side and enhances and grows and moves around to the dawn flank. And what Don's done here, if you can see this, is he's kind of superposed the UVIS auroral images into the center of the image over the top of Saturn. And you can see there's kind of a striking counterpart signature in the ENA intensity, indicating that there's linkage, obviously, between the magnetosphere and the ionosphere, but they will also maybe can learn something about the auroral source region from looking at the ENAs as well. The extent of this, sorry, I should have said, we're looking out to around Titan's orbit here, the outer thin white line. But they're quite difficult to use, the INCA images as they were released at that point. Jim Carberry did a lot of work trying to track these things that rotate around the magnetosphere. And to do that, he used kiograms. So some of you will be familiar with auroral kiograms, where you construct using radial profiles how things develop in universal time on an x-axis and local time on a y-axis. And things that have positive gradients are things that are rotating about the planet or the ionosphere. In this case, it's around the magnetosphere, of course. So we know from this kind of analysis that these ENA enhancements, they sub-co-rotate around the planet, probably about 60% of rigid co-rotation. And he did this for many of these tracks, and you can see this kind of, I call it the children's crayon plot. I don't really like it very much, but it's an early effort at trying to track these things in around the magnetosphere and say how fast they go. But really, it's a computer vision problem. When you construct the kiograms, you also lose information about the radial motion as well. So it's not ideal, but it's what we had at the time. So I tried to do this, excuse me, I tried to make some of these kiograms myself, and we also found a really nice long UVIS imaging sequence, so we could try and really pin down the local time signature in the aurora and in the magnetosphere. So on the left here, you have an ENA kilogram based on the equatorial projections. So universal time on the x-axis, local time on the y-axis. And you can see these kind of 3 injection signatures here, one of which has come all the way around the planet. And we try to match these things with injection features in the auroras at the same time. So on the right-hand side now, based on the UVIS images, we have a coincident kilogram, and I've kind of overlaid on top of these the ENA tracks as well. So you can see that 2 of the ENA signatures have clear auroral counterparts, but one of the very clear auroral signatures did not have an ENA counterpart at this energy. And I think probably that's because INCA isn't seeing the whole ion distribution. That's something that will change with JUICE. They've made instrument advancements, so when they get to Jupiter, we'll start to see much lower energy ions and subsequently ENAs as well. That's my theory anyway. But at that point, I was kind of frustrated by making these projections was quite computationally tricky, and the whole data set wasn't really homogeneous. It was quite difficult going from PDS straight to an equatorial projection. So we went back and worked with Don Mitchell and Chris Paranicus at Johns Hopkins. And very quickly here, we just essentially reprocessed the entire INCA data set. We recalibrated everything. We ray traced every single image, and we projected everything into a nice, clean, calibrated data set, recalibrated. If you want to use that, just get in touch. There's a few papers that go with it. But the important thing to know is that INCA took a lot of images, 670,000 sort of 4 to 5 minute exposures. So a really successful data collection campaign, but a super underutilized data set, which we're starting to change. But the key thing to note is in this data set, we've binned every single pixel through the entire mission. It's not an image-based analysis, it's a pixel-based analysis. So there was a lot of ray tracing and supercomputing. And this is one of our first sort of nice results. So Jim Carberry had already attempted to profile the statistical morphology of Saturn's ENA emission based on 44 days of orbits back in 2007. And you can see when we use the entire data set, we can improve on that. And we have 4 panels here looking down on Saturn's magnetosphere with the sun to the right-hand side in different energy bands. And you can see these ENA tori that are really beautiful and striking. And they're a direct result of this water cloud and these injection events that get the dynamics here are smoothed out in time, but we get instead these pictures of the extents of the ENA cloud. And there's also an offset towards the day side, which is probably related to ion trajectories being affected by an E field asymmetry. I'm not talking about that today, but there's some cool other things as well that came out of this. So I wanted to really look at, we have this nice data set now, we can see stuff moving around. So I want to try and contribute to the picture of the dynamics we have in the flow velocities. So getting that kind of stuff out of the ENAs is the next step. And what I mean by that, you can see here in Rob Wilson's plot. This is based on in situ measurements from CAPS and things like that. And it's flow velocities from forward model fitting to ion data. Michelle Thompson's also got some moment-derived velocities. So really kind of filling in this picture with the INCA images is something that we're aspiring to do. But it's a computer vision problem, as I've mentioned. We've fixed one issue, which is the getting the data set into a nice workable state. And the next thing is actually tracking these things systematically that we can see with our eyes, but actually getting traces out with the computer is difficult. So we are trying to get Voronoi segmentation working, which is a computer vision method. And it's inspired by Patrick Geo and Nick Kilios's voice algorithm, which I think I've failed to reference here. Apologies. But yeah, Will Rhodes was a master student we had last year, and he got this working on ENA images, which is really cool. So rather than kilograms, we can track basically the voice algorithm. It hones in on areas of intensities in an image that are similar, and it kind of iteratively does this, and it comes to a point where you say, okay, my neighbors are all the same as me, so I'm going to stop. And you end up with this seed cloud, which we can track in time. And it's kind of more useful than a kilogram because we get radial information and we get azimuthal information out as well. So you can see here we've successfully picked out this thing moving around the planet, and then we can get distributions of the radial position and how that changes in time. The error bars here are the extents of the cloud in radial distance and local time respectively. So we have a rotation rate tracked and we have the radial position tracked as well. And we're working on a kind of survey of this at the moment. We're going to get some event dates out and things as well into a list. Another thing I wanted to touch on just before we leave Saturn is a few other aspects of magnetospheric dynamics that we can pick out with ENAs. So early on in just after Cassini's arrival at the Saturn system, Chris Paranicus produced this really nice research letter where they see the ENA intensity oscillating with planets Saturn's rotation period. We think we've figured that out now. It's a combination of a viewing effect at low latitudes where if you're in Saturn's equatorial plane, some of the hot plasma is rotating towards you on the dawn side, but it's moving away from you on the dusk side. So you have this kind of energy Doppler shift called the Compton-Getting effect. So it's partly that, and it's partly also that the plasma sheet is thickening and thinning periodically as well. So I'll show you another plot in a second, but essentially the whole magnetosphere is going through phases of thick and thin plasma sheet, which is basically producing more ENAs in certain phases. So there's that rotational modulation as well. And Don Mitchell on the right-hand side here, that this was kind of a footnote really in his very cool book chapter on these injections. There's a nice correlation with narrowband radio emissions as well, which is something we're looking into, and it's probably related to the fact that the hot plasma is being injected into the system, and then it's making these temperature anisotropies that are required for these plasma wave emissions. So this is different to the cyclotron emission. This is a plasma mode that we're just starting to understand. I've skimmed over that massively. There's lots of work that's been done on that at the moment. But just to finally clarify that this long-term picture at Saturn, these are the kind of profiles we can get when we stare at a magnetosphere for 14 years with an ENA camera. We have local time profiles on the left-hand side. We have radial profiles in the middle for different energy wavelengths. So sort of peaking between 7 to 10 RS, depending on the energy. And that's a function of where the neutrals are, where the neutral density is peaking, and also where these hot ions are getting into as well. And the right-hand side, these sinusoidal responses, this is the global ENA intensity changing with this planetary period phase. Sorry, Rosie, I said I wouldn't mention planetary period, but you can't really get away from it as Saturn. I'm going to skip over that because that's just a couple of kilograms showing this radio ringing with the ENA kilograms as well. There's this basically as it passes through the dusk sector, we think it's kind of this is the point where the injection has got in so far that it starts to meet maybe colder plasma and produce these temperature gradients, kicks off this radio emission. So moving on to Jupiter, I think we're about halfway through. Jupiter's different because it's charge dominated. So famously, it has a very intense radiation environment, and we'll talk about why that's important or different for ENA emissions. But Cassini INCA actually first detected ENAs at Jupiter rather than Saturn before it got there. So in 2000, it did a flyby, and on the left-hand side here, that kind of red dot is Jupiter as kind of a point source from 0.5 AU. And as they got closer, it started to resolve. So 350 RJ out, they start to get some more structure. And then 200 RJ, as well. So this is kind of 50 to 80 keV hydrogen images from INCA. And we thought at this point that it was the exosphere and moon sources, so mostly Europa, but a bit of Io as well. And then Barry Moog did a really cool thing where they used a much more distant measurement at 800 RJ, where Jupiter will be a point source. And they used this in space to quantify the point spread function of INCA, which is something they couldn't do at Earth testing. And then they deconvolved the previous images. So that's just a nice little bonus plot. That's a really cool paper if you want to go and check that out. So I'm not really a fan of flow diagrams, but this is a really nice paper by Fran Bagan and Pete Delamere where they compare the Jupiter and the Saturn systems. But the bit I want to pick out here is the difference in neutral dominance at Saturn over charged particle dominance at Jupiter. They both have obviously things in common, Jupiter and Saturn. So they're rapid rotators. They have plasma sources deep in the magnetosphere. This plasma has to escape radially through things like flux tube interchange. But the neutral ion ratio is several orders of magnitude different. So why is that? And it's kind of to do with differences in electron impact ionization. So Saturn has this distributed neutral cloud, and it's almost this perfect emission screen for neutrals. So I'm just going to move my window out of the way so I can read my own slide. Sorry, runny nose. There's a much smaller fraction of Saturn's neutrals near the source that become ionized. And this is to do with slower co-rotational flow near Enceladus, which has a knock-on effect right down through ion pickup temperatures to producing a cooler thermal electron population. And essentially, the ionization of water products it peaks with electron energies of up to about 100 eV, but at Enceladus, they're around about 10. They sit around at 10, so the ionization is really slowed, which allows the water to spread out through the system. It doesn't get ionized quickly. Whereas at Jupiter, oh, I've skipped ahead. Yeah, at Jupiter, the electron energies are much closer to where they would ideally ionize. So a small difference of maybe several tens of eV in electron temperatures has this huge implication for the rest of the magnetosphere being either almost filled entirely with radiation belts at Jupiter to being much more neutral dominated at Saturn. And the effect that has on possibly what ENAs are going to look like is that the moon structures might be more distinct. They might be more short-lived because of mixing and chemistry and things like that. But essentially, we won't really know that until JUICE gets there. The very cool thing about JUICE is that it looks really similar to the INCA camera. You realize how good the INCA camera was first time, except they have a better image spatial resolution. They've done something very clever with the slit. They have a slit that they can rotate, and it has different aperture sizes. They can tune the spatial resolution, which INCA didn't have, and a much wider energy range. So they're going to see down to a few keV, whereas with INCA we saw maybe down to about 25 keV. It's also designed to operate obviously within Jupiter's harsh radiation environment as well. So even as far as Ganymede, I've not touched on moon interactions in this talk, but there was a very cool Titan interaction paper that Don Mitchell did as well. So INCA went very close in on moon flybys and saw ENA emissions associated with Titan's exosphere, and Ganymede is probably going to have ENA emissions associated with it as well. We do know the imaging we have from Cassini, that's the only images we have of Jupiter, but Barry Mock has done some in situ kind of indirect detections using Juno instruments as well. So we do know that Europa and Io Tauruses plus the planet itself emit ENAs at Jupiter. So yeah, that's going to be very cool when JUICE gets there. So the big question really as well is that people are starting to become interested in, obviously for obvious reasons with missions planned, is that do the ice giants emit energetic neutral atoms? And it all hinges really on what we know from the Voyager flybys, and are there enough neutrals and charged populations present at these very weird asymmetric magnetospheres that might support an ENA emission? So some mission proposals are calling for ENA instruments, like the Neptune Odyssey proposal, and others instead are questioning whether the moon sources are going to be strong enough to give us a reasonably detectable ENA emission. So it's a very open question. some of you may have seen Jamie Jasinski's very cool paper that said that the Voyager flybys went past Uranus in a very atypical state. So that gives us maybe a bit of hope that maybe the ion energies are higher than maybe Voyager saw, which is good if we want to detect an ENA image. Dan Naylor at Lancaster is he's working on improving neutral models for the ice giants for figure out X-ray emissions, but that can very easily be adapted to ENA production models, hopefully. So we're starting to think about that. And this is just a simple moon source neutral model that Chris Arridge and George Chester has put together. So this is based on the Chen profiles that are from Voyager 2. So you can imagine the top here is just a simple torus model with things like boost factors and scaling factors, and then the bottom one is a fake integration from an arbitrary spacecraft distance. So when you combine that with an ion production model, you can maybe start to simulate ENA emissions as well, which is what we're starting to think about. It will be extremely useful at the ice giants if we can get an ENA emission, because I was saying to Rosie just before this started, if people think that Saturn's periods are complicated, when we get to Uranus and Neptune, they're so axisymmetric that there might be a situation, this is how I think about it, where the plasma toruses, which are bound by the magnetic dipoles, are going to be interacting at different places in the magnetosphere with the neutral torus, which is obviously spin aligned. So there might be flashing of ENAs at different phases or different periods of the day even, and there's going to be seasonal effects. So having this global photograph of where this charge exchange is happening would be very useful at the ice giants, particularly on approach. So I hope that we can sort of figure out some good simulations and instrument requirements for potential ice giant instrumentation. And something I'm definitely not touching on because I don't understand it right at the end of this talk is ENAs can be very useful for imaging the heliosphere. So this is where solar wind, the very edge of the solar wind, interacts with interstellar space. And this is something that Cassini INCA did as well, amazingly, very successful instrument. With this Cremigas paper, you can see on the left-hand side. I think the top one is a galactic projection or an ecliptic projection. The bottom one's a galactic projection. I'm not used to looking at these kind of frames at all, I'm afraid. But you essentially are seeing here the nose and the tail of the heliosphere. And it kind of becomes quite philosophical to me. It's a huge magnetosphere sat in interstellar space, essentially. But the ENAs can tell us about the shape of the heliosphere. And one of the things that fell out of this paper was that it was previously thought that the heliosphere was kind of a comet-like shape that's being distorted by the sun's motion through the interstellar medium. But this kind of ENA plot apparently completely debunked that. Instead, we have this complicated ribbon structure emerging from IBEX images, which I don't understand. There are 6 different explanations proposed in that paper, which I'm not going to attempt to relay to you. But I will refer you to Tim Horbury's previous MIST seminar. I think it was a few seminars ago, but that's definitely worth a watch because that talks about the IMAP mission, which has got an entire suite of ENA images, which is going to be very cool for studying things like the heliosphere. So I think I've raced through it a bit. Apologies because I can't see my notes, but I wanted to leave you with a few open questions related to ENAs, which are, I mean, essentially very open questions. There's a few Saturn-related ones. So we're still thinking about how Saturn's ENA emissions relate to auroral signatures. Whether this partial ring current that we're seeing in the ENAs has field line currents at either end of it, or it's distributed throughout, and then that maps into the auroras. And also what's driving the PPO modulation of Saturn's ENA emissions. I think we've got a handle on that, but there are a few more tests we can do, including whether there's solar wind compression control. So this hasn't been tested yet, but I think what might happen at Saturn is that a solar wind compression will force dayside trapped ions into regions of higher neutral density. So there might be this kind of dayside enhancement as well, which we haven't really quantified yet because we're so often looking at things that rotate around. We're not looking at fixed local time stuff. So that's ongoing. And yeah, a couple of big questions at the end. What will Jovian ENA morphology tell us about a charge-dominated magnetosphere? And do Uranus and Neptune have ENA emissions? It might well be that the norm for planetary magnetospheres is that they're asymmetric, hugely asymmetric. So if these things have ENA emissions that can help give us wider context, then it's an exciting time, hopefully, to be flying with future ENA instruments. I think I'll finish there.